All right, everybody. Hey, welcome to Mondays with Mike. I'm Fox 26 Chief Meteorologist Mike Iskovitz, and I want to thank you for joining me here for this edition. Now, depending on when you're watching this, I just want to let you know that if there's ever active weather that's happening, remember you could always check in with your Fox 26 weather app. So just head to the App Store, Android or iPhone, just search Fox 26 weather because you will find Fox 26. You'll find Fox Local, which is also great to download. But the Fox 26 weather app will give you immediate access to the radar. So you can track what's coming your way. You could also look at a future radar. You can look at the satellite to see if there are ever any tropical systems out there. You could track them that way. And there's even a feature on there when you go to overlays. It'll say, I think storm tracks is what it is, and it'll label each individual storm according to how strong it is, and you could actually click on it, get some data about the storm, how fast it's moving, and things like that. So that's on the Fox 26 weather app. So like I said, if there's ever any active weather, whether it's happening right now when you're watching this or any other time, go ahead and check in with your Fox 26 weather app. So recently, I did a talk to the Science National Honor Society at a high school in the area. And I realized, I've never really made a strictly uh, all about meteorology Mondays with Mike segment. And so, if you have kids that are interested in meteorology, especially older, but even if they're younger, they might find it interesting. But even if you have kids that are interested in meteorology from especially, I think, middle school, high school onward, where they're really kind of serious about it, or even early college and you know, they want to change majors. I have some information for you. This is sort of basics of like what do we do? How do we do it? What are some of the tools that we have? A little bit of the history of meteorology. So I hope you'll find it interesting. I enjoyed putting this together. It took me a while, so I wanted to share it with you. So I think the high schoolers actually did not fall asleep. They actually had a couple of questions at the end, which made me happy. And so, yeah, let's go ahead and take a look at it. So I'm going to share a PowerPoint that I made with you. Let me go ahead and share the screen, and we shall move on from here. So here we go. Here's my PowerPoint that I made. So obviously the topic is meteorology. And let me see, can I hide this? I don't know if you're going to see that, but anyway, so this is the topic of meteorology. So what is meteorology? There are a lot of different definitions, actually. Some are simpler, some are more complicated, but I kind of narrowed it down to this. It's the study of the physics, chemistry, and dynamics of the Earth's atmosphere. The goal of meteorology ultimately is the complete understanding and accurate prediction of weather. So, just to summarize that, it's the study of how the atmosphere, how the air moves around, how heat moves. We call that thermodynamics. Um, the water cycle, how terrain interacts and causes the formation of thunderstorms, the movement of the oceans, the transfer of heat from the oceans. There's even the study of the upper atmosphere where weather doesn't occur. So there's a lot in meteorology. There are a lot of little branches of meteorology, but in general, the bottom line is we are looking to most accurately develop technology to help us predict the weather the best way possible. So that's that. As you can, probably know that. All right. So let me make myself a little smaller here because I've got a couple of guys here on the screen. Why do I have them? Why is it called meteorology? Well, the guy who's in your upper left, you may recognize. His name is Aristotle, and he was one of the great ancient Greek philosophers. And he really is the father of meteorology, sort of. I mean, yes, there were a lot of great thinkers through antiquity and since the beginning of time, but he was the first one to really put it all into a book in ancient Greece. So this is going back 2,000 years or so, maybe a little more than 2,000 years. And he was the first one to write a book, and it was titled Meteorology in Greek, Meteorologica. And the gentleman in the upper right-hand portion of your screen, up there, his name is Pliny the Elder. Very, very important figure in Rome. There was Pliny the Elder, Pliny the Younger. The reason he's important is that he took a lot of the knowledge that we got from Aristotle and others, and bunch of others, and put it into a book of history and science. It was sort of like he was the first person to write like an encyclopedia for the Western world. So a lot of the weather observations and knowledge that came from ancient Greece got translated from Greek into Latin by Pliny the Elder. So why is it called meteorology? This is like Seinfeld. I mean, hey, why do they call it meteorology? You're not talking about meteors, right? Well, in ancient Greece, I don't speak Greek, but in ancient Greece, I've told, according to the internet, that meteoros meant lofty, something that was high in the sky, meteoros. In fact, it just occurs to me that if somebody really has a big rise to the top, they call it a meteoric rise, right? Which is strange because meteors come down. But anyway, so that might go back to that original definition, high in the sky or lofty. Now, during the time of the Roman Empire, in that stage of Latin, meteorum was a thing that was in the sky, or meteora, I think was the plural, things that are in the sky and things happening in the sky. Now, through the years, as all of that got translated into other languages around the world and around Europe, in English in the mid 1500s, it began to more regularly refer to atmospheric phenomena or weather. So that's where this word meteor was really anything that was in the sky. And so in modern usage, a meteor describes natural things that are in the sky or falling out of the sky. And so a meteor is a space rock that falls through the sky. And so that's a meteor. But lots of other things are called hydrometeors. Coming from the word hydrogen, which makes up water. So a hydrometeor can be a raindrop, snowflake, cloud droplet, fog, hailstone, anything involving water in the sky condensing to a liquid or to a solid is a hydrometeor. So whenever it's raining, kids, if you want to impress somebody, or if you want to frustrate them, I don't know, either way, if it's raining out, you could talk about how all of the billions of hydrometeors are falling out of the sky. Got it. All right, what about education? Well, I could say for myself, I have a Bachelor of Science in Meteorology from Florida State University, which is a school that's getting better and better and better, harder and harder and harder to get into, which makes me happy. The football team stinks. We were dominant for such a long time, and we're having a hard time negotiating this portal thing and the NIL deals, and it's college football is weird these days. But anyway, that's neither here nor there. On the subject of meteorology, Florida State is great. Texas A&M is great. The University of Oklahoma is great. You've got a lot of other big schools. Penn State is really good. The West Coast schools, I don't know that well, but I'm sure there's some really good ones out there as well. And there's lots in between. So bottom line is you find yourself a good school where you can major in meteorology. That's my number one recommendation. There are some other routes you can take. You can get a degree in a related field. Some people get a degree in journalism or geography or something like that, and then go on to take a 2-year online course and get a weather broadcasting certificate. And that's great too. A lot of people have done that. I went the traditional route. People who really want to be scientists will typically get a PhD. Some folks can be professors and do research and everything else with a master's degree. Most, I think, will go on to get a PhD. It is an extremely, extremely intensive field, meaning this is not for the faint at heart. You're going to have a lot of math. Even just to get the bachelor's degree, you're going to have a lot of math. But if you go on to get a master's or PhD, you are going to know these gigantic equations like you would never believe. and not just know them, but explain what they are telling us about the atmosphere. So, um, to get my degree, which was just a 4 year bachelor's degree, I had to take 3 semesters of calculus. So calculus one, two, and three. I also had to take a course called engineering math or e-math, which I took with my friend Patrick Blood, who now works for the National Weather Service in Hawaii. Nice assignment there. Um, and the teacher also worked for NASA. He would leave for the class for a week because he had to go design rockets or something. That's how smart this guy was. He was a Vietnamese guy, and he spoke with a fairly strong accent, which made this, what I'm going to tell you, a little bit funnier, which was he would make fun of the bad grades that everybody was getting. I mean, we would try so hard, and the coursework was so difficult, and he would say, "Come get your Fs." Boom, and he would just slam all the exams down on the desk, so that everybody would come on. Not everybody got an F, but that's what he would say. It was hilarious. But I ended up getting a B plus in the class. I don't know how. It was an extremely hard course. And then, of course, the engineers had to take engineering math too, and then more. There's also math involved just in the weather courses, like atmospheric dynamics. Dynamic just means move, how the air moves. So there is a lot of math involved in that. All the calculus that you learn and some of the engineering math, which is also called differential equations, is used in those atmospheric science courses as well. And then thermodynamics is a very fancy word for the transfer of heat. So they also call it atmospheric physics. That was a hard class. That was a really hard class. I still remember it. Man, that was hard. Okay. So as meteorologists, how do we know what's going on? I mean, how do I just walk into work and know what's going on? People used to ask me, they're like, well, don't they tell you what to say? And I'm like, who's they? What do you think they are? What do you mean they? They are people like me. I'm the they. So anyway, how do we know what's going on? We have a lot of tools that are typically run and maintained by the United States government that allow us to track weather, both on a very large scale and on a very small scale. So like we could see the whole globe with satellites, and we can see the city of Houston with our radar. So and everywhere in between. So we'll start out with GOES. Very, very important. It's the biggest innovation that's happened, that has allowed us to track hurricanes, to track big storm systems over the last several decades. The first weather satellite was launched and became operational in 1961. Since then, since the late 1980s, I believe that was when we launched our first GOES satellite, we're now well into the latest generation of GOES, which is about the 18th GOES satellite, I think. 17th and 18th are up there now. GOES stands for Geostationary Operational Environmental Satellite. They don't orbit near where the International Space Station orbits. They are extremely far away, more than 22,000 miles up in the atmosphere. And that's for a very good reason, which is that the International Space Station will orbit the Earth every 90 minutes or so. We don't want that for a weather satellite. We want it to be over the same location all the time. And so it's placed very far off into space so that it orbits the Earth once every 24 hours. And the Earth spins once every 24 hours, give or take. All right, couple seconds. So as the Earth turns, the satellite goes around at the exact same rate, which means that the satellite is fixed over 75 degrees west longitude. So it is there all the time over the equator and 75 degrees west. And it takes pictures, which is how we can track hurricanes moving across the Atlantic and so forth. So yeah, it is an amazing piece of technology that senses a lot of different things. Okay, so the GOES satellites are invaluable, and they do have multiple imagers, which is sort of like a fancy way to say camera, but unlike the camera on just your iPhone or traditional camera, it can see more than just visible light. It can see different wavelengths in the spectrum. For example, infrared light. And the reason that's so important is that without infrared, we wouldn't be able to see in the dark. So if all we had was visible satellite, we could only see the clouds during the day when the sun was overhead. But with infrared, we could track it 24/7. And what it's actually looking for, like when we show you the satellite view and we can track a hurricane, and sometimes it turns into those bright colors that we highlight for you, that's an enhanced satellite view that we use a different um, color to designate temperature. So the colder the temperature is, the stronger the storm is. And that might sound odd, but it means the taller the cloud top is. So if a storm or a hurricane grows very, very tall, then it's going to hit the top of the atmosphere, what we call the troposphere, and will get very, very cold. And so that's why the brightest colors on the satellite correspond with the coldest temperatures. And by the way, these GOES satellites also have other sensors on there to track the sun and things like, bursts of X-rays and things like that. So they have a lot of other sensors on there. All right, next is something that you've seen on TV all the time, and that is radar, specifically NEXRAD Doppler radar. So they're located all around the country. We have one here in Dickinson. Technically, it's called League City, but it's like right on the border, League City, Dickinson. And so that's our primary radar for our area, but we also have nearby, we have Lake Charles radar, we have Corpus Christi radar, we have radar from Killeen, and we have radar from San Antonio. So we're pretty much covered. Fort Worth. So we're covered from the north, south, east, west, and then of course, we have what's happening on top of us. And so that radar has gotten more and more sophisticated over the years. It now has the capability of not only tracking rain, but it can track whether the raindrops are moving toward or away from the radar and how quickly they're doing that. So we use that to detect rotation. They also can track the size or the shape of hydrometeors, the shape of like hailstones and things like that. And we could use what's called the dual pole technology to determine the type of precipitation. And also, by the way, it can also help us to recognize things like debris if a tornado has touched down. So it can actually see that. Other radars, before this era were never able to do that. So we also have our computer models, which again, I mean, we'd be lost without the computer models. We would only be able to do very short-term forecasting, just like they kind of did in the older days of meteorology, back like going back a couple hundred years, but then especially the early part of this century, mid part of this century, we didn't have models that ran, we didn't have computers like we have now. Is that you would make a map or a chart, and that would be based on pressure observations from around the country. And based on high and low pressure, you would be able to draw where the low is and draw where the high is and draw where the front is. And based on the shifting winds and the time of the year, you can kind of try and estimate how fast the front is moving. And that way you can kind of try to predict, like today, approximately what time it's going to be raining. Obviously, it wasn't to the, quite as accurate, I don't think, as we are now. But if you knew that it was either going to be sunny or rainy, and you're pouring concrete or something, I mean, that doesn't make a big difference in your life. So we've known how to do that for a long time. It's just way easier now, especially, and we can go way farther out also. The other question that this is going to answer is the last one, ASOS. That stands for Automated Surface Observing System. Everything in meteorology is an acronym, so ASOS. This is why we always tell you what the temperature is at the airport. It's like, if you really think about it, you might ask the question, like, why are they always telling me what the weather is at Bush Airport? Like, I don't live at Bush Airport. Well, because that's where these ASOS stations are located. And it's because airports, it is absolutely, life threatening if they don't have accurate weather information. So the FAA and NOAA will place and maintain and calibrate the equipment that's located at the airport because it needs to be as accurate as possible. And that's where these things are going to cost a lot of money. Yes, I could put a weather station in my backyard that I can get for $100 off of Amazon, and it'll probably be pretty accurate, but it's not going to be precise like what they have at the airport. So that's why that's where we get our data to verify what the high temperature was for the day, for example, what the strongest wind gust was, what the humidity is, and very important for pilots to set their altimeter. So they need to know what the pressure is exactly. And that's how they know their altitude. So that's why we get it from the airports, because that is where the most sophisticated equipment and the most maintained equipment is located. All right. Weather satellites. Well, weather satellites are launched into space by a big rocket. The one that's on the left-hand side of your screen is not the Falcon Heavy. I think I took a picture of the Falcon Medium rocket. But anyway, it's that United Air Alliance, Boeing and teaming up with some other companies. Anyway, they launch these things into space, and they have to have a capability to get it up to 22,300 miles above the surface into orbit. And you'll see there are two GOES satellites that cover the United States, and in fact, our whole hemisphere. Goes east and goes west. Goes east covers the East Coast, goes west covers the Pacific Ocean and the West Coast. So if we didn't have those, we would definitely be lost. Doppler radar, you'll see that we have a loop there of Hurricane Beryl, a picture in the upper left-hand corner of what a Doppler radar tower looks like. The lower left-hand side shows a hook echo. That's a reflectivity, basically like not Doppler. It's just showing where the raindrops are associated with a tornado. And then you can confirm that with this very, very tight area where you have the red and yellow, which is raindrops moving in one direction, right next to this green and blue where the raindrops are moving in the other direction. That's the twist. And then we also have this two waves moving like this, which is what's called the dual pole radar, which allows us to determine precipitation types. And then finally, we have our weather models that are extremely sophisticated computer programs, way over my head. I mean, I did take a course in what's called NWP, which is numerical weather prediction. It is brainiac level stuff. I can tell you the basics, which is that there's a part of the model that has to ingest the data assimilation from all the ASOS stations, from satellite observations, from ship observations, from airplane observations from all over the world, have to take that and bring it into the model, which is a feat in and of itself. Then the model has to run all of the equations for it to make a global model for a 16 day. I mean, it's beyond belief. And we weren't able to do it until we had supercomputers like we do now. So if you just wanted to run this on your regular PC, it would never work. But you could run a very simple, smaller model on your PC. And there are ways to do that too. I've never done it. One day I want to try to do it. So yeah, weather models are extremely complicated. There are a lot of them. Each weather agency has their own model. For example, there's the American model, the GFS. There's the European Center for Medium Range Weather Forecasting, also known as the Euro. Germany's developed their own model now called the ICON. There's a JMA model, which is the Japan Meteorological Agency. And there are plenty of others. The Canadian model is called the CMC. So there's a lot, and we use a lot of them on a routine basis. So that's the overview. This is a look at what those ASOS stations look like, by the way, at the airports. And it's kind of neat. Like this one, the one that's in the top middle portion of your screen is called a celiometer. That one measures the cloud heights, which is obviously very important for pilots. The one here in the lower right is a visibility sensor. It like sends laser beams back and forth to test fog. This one in the upper right actually is a thermometer, believe it or not. And this tall tower, at the top of this tower is a anemometer. It measures wind speed, but it doesn't spin around like the anemometers you've seen. It's called ultrasonic, I think. It uses sound waves that it bounces back and forth between its like three sensors, and that helps to detect how the wind is flowing. It's kind of really interesting, actually. is more accurate than the other style of anemometer. So here's a look at some common questions for me. Like if I were at a career day, or like I said, talking to, kids that are maybe interested in becoming meteorologists, maybe your grandson, granddaughter, son, daughter, brother, sister, whatever that is. So when did I know I wanted to be a meteorologist? August 1992, when Florida got hit by Hurricane Andrew, and I was there watching all the weather people on TV. Is AI going to take my job? I don't think so. No. Well, you never know, but probably not. But I think it is going to make forecasts more accurate. I also think we're going to use AI to spot tornadoes and things like that too. Is my job fun? Sometimes. It's okay today. Some other days are not as fun. Do we get backstage passes to Sabrina Carpenter? No, not at all. And how does it feel when your forecast is wrong? Well, it feels just about the way you would think it feels. Not good. But that's why I try not to get the forecast wrong. And the thing is, it just, if the forecast stinks, the forecast stinks, but which I'll probably, do my best to tell you on the air, like, hey, there's a lot of uncertainty with X, Y, or Z. So anyways, I hope this was helpful. Maybe share this with somebody who, has a teenager that might be interested in meteorology and they want to know a little bit more, or, anything like that. Teachers, maybe you could show it to your class. So anyway, thanks for joining me here for this little bit of a different edition of Mondays with Mike. Shout out to my mom and my brother. Hope you guys are doing great down there in South Florida. And we'll see you all next time. Bye-bye.